How are you all today?
Great.
A couple of things that I want to mention before we get started. I did put the old 5.1 notes that accompany the video. Hopefully everyone had a chance to watch that. Did anybody watch it?
Yeah, I did.
Okay. So if you didn't, the video is with all of our other lecture videos, and that's sort of gotten buried here in this announcement. It's like the third announcement on the main page. So you do want to look at that. I also, if you watched the video, you saw that there's a lot of summations that come up. So I did post a link to this summation calculator here. The sums in 5.1 are all finite sums. In 5.2, we'll start looking at infinite sums.
Are we going to have to memorize that?
No, the summation formulas you need to know. So I did reference I have a handout I'll pass out in a minute, but I did reference in 5.1 that there was a quicker summation formula for the limits and stuff. We'll look at that, but you either need to know the summations on this handout with the infinite limits, or you need to know the summations from 5.1. So the summation formulas were the sum, like k equals 1 to n of some constant, and that was c times n, and then the sum of the first n numbers, like 1 plus 2 plus 3 plus 4 plus 5, etc., n plus 1 over 2. All of those, I think there are 4 total. You need to know those, or I prefer the shortcut that's from this handout. It's not actually a summation formula in our textbook, but it does lend itself to an easier computation when we're looking at area under curves. Okay. So I'll pass that out in a little bit. But for 5.1, if you have another summation on your calculator or whatever, use whatever you want. This is just here for those that might not have that resource on their calculator. And like I said, the sums we deal with in 5.1 have k equals 1 to 50, and so it would be k minus 1 over 25 cubed plus 1. You're just using this. Desmos is automatically assigning n. I don't know if there's a way to change that. So you want to make sure that you're typing in, an expression for n instead of k, like you would have in your homework. But it's all the same. Okay. So if you have any issues or questions on 5.1, please let me know. Issues with like some summations and stuff like that. It's really tedious stuff, but it is building the foundation of what is chapter 5 and what is integration. Did anyone have any questions on 5.1? It's a lot of content in 5.1. And really the summary of 5.1 is how do we find an area under a curve? We fill it up with rectangles, and then we just add the area of all of those rectangles. But then the tediousness, I think, was the notation that surrounded how we do all of that. But by and large, that's all you're doing. And we refine that as we move forward. But the idea in 5.1, minus the notation, which is sort of cumbersome, is that to find an area, initially, we're just filling up a region with rectangles and adding up the area of each rectangle. So that's pretty much the summary of 5.1. You saw in 5.1, there was different types of Riemann sums, depending on where we wanted to evaluate the rectangle. So please look at that video if you haven't already. We will still reference some of those things as we move forward. And in 5.2, we're going to start to look at definite integrals. I didn't use the language when we were in 4.9, when we found the antiderivative. I tried to be consistent and called it just the antiderivative. But the antiderivative is a type of integral, and there's 2 types of integrals. Here we're dealing with a definite integral. The antiderivative is what they call an indefinite integral. So as we progress, I'll make sure to mention the difference between those 2 things. But in 5.1, what we saw was we found areas above the x-axis under a function, and so all of those areas came out to be positive. But there's nothing saying that, if we had a function like whatever this function is here in this figure, if we looked at, say, the area from 0 to 3, that some of the area is above the x-axis and some of the area is below the x-axis. And we know when we talk about area, it doesn't make sense to say we have a negative area. So if this is the case, so the Riemann sum for this first figure on the left is negative 6.625. All that's telling us is we've got an area of 6.625, but it's below the x-axis. It's almost like a vector or a velocity, right? The negative here indicates that it's below the x-axis. If you have a positive area, like this area in green, then we know that's above the x-axis. But that figure to the right, we would say, well, I've got a positive area above, and I've got a negative area below. In order to get the total area, I have to add the area above minus the area below. Right? So what that actually gives us is what we're going to refer to as the net area. So we have regions above the x-axis and regions below. And in general, when we find or compute a Riemann sum, depending on what the function looks like and where the areas lie, the most general statement is we have a net area when we compute that. So, I don't know, let's put in specific numbers here to get an idea. Let's say this area on the left is 3. The area below, whatever color that is 8. And this area on the far right is 7. So if we were to sum all the way from A to B of this, whatever this function is, we would have the area 3 plus the area of 7 minus the area 8. So this is above the x-axis, and this is below the x-axis. So that's sort of what the definition's telling us. The net area of some region is the sum of the areas that lie above minus the sum of the areas that lie below the x-axis. Okay. So here it's implicit here that the areas that are above and below are both positive quantities. Area is a positive quantity. Okay, so the sum of the areas above minus the sum of the areas below. We see that here, 3 plus 7. We can view that as plus negative 8 if we wanted to. But this right here is the net area. The net area is no more than the contributions of the area above and below the x-axis. That's all it is. 3 plus 7 is your earnings, and 8 is what the government takes away. And that's your net. Okay, so are there any questions on that notion of net area? Hopefully it's pretty straightforward. Okay, so what we want to kind of put this to now is our Riemann sums. The Riemann sums give us net area. Now it's just a general statement. If all of your area is above the x-axis, the net area and the area is the same in that instance. We just mean in general when we compute a Riemann sum, it's the net area. And a lot of times we just compute this. We don't really look at. There's certain cases where we do look at the function or its graph and see, well, which parts are above and which parts are below. But for us, usually we're just computing the area. And we say, okay, well, this is the net area, and move on. We don't really look at the graph and try to determine what's above and below. All right, then. Everybody okay? Move on. So we sort of alluded to this in the last section in 5.1, in that how do we make Riemann sums exact? Because Riemann sums at this point are mere approximations to the total area, or the net area. So does anyone remember how do we make the Riemann sum exact?
You average the left and the right?
So if we averaged, we would get a better approximation, but it's still an approximation.
More partitions?
Yeah, we would have more partitions. So let's just remind ourselves, the Riemann sum in sigma notation is defined as the sum from k equals 1 to n. So it's a finite sum. We're stopping at some number n. And then we evaluate f of x star. This is my stars are really bad. F of x star sub k times delta x. Also, let's remind ourselves what that actually means. What is all that stuff? So the sigma is just indicating that we sum all of those things. The k being 1, this index here is always a counting number, 0, 1, 2, 3, 4, 5. It's never any other kind of number. So this is just indexing these sub k's right here. So we have, this was f of x star sub 1 times delta x plus f of x star sub 2 times delta x, and so on, right? So it was just a compact way to write f of x star delta x plus, right? But what is the f of x star referring to?
Is that the initial starting point or something like that, or the base?
So the initial starting point would actually be, we start with x sub 0, and we end with x sub n. So we end with this is our endpoint on the interval AB, if you want to think about that. On the interval AB, if we said approximate the area from 5 to 12, then we would start with x sub 0 equal 5, x sub n would equal 12. Like I said, the area is just the area of rectangles added up together. So we see this right here, that's the area of rectangle number 1 plus the area of rectangle number 2, right? So the f of x star times the delta x gives us the area of each rectangle. And how do we define an area of a rectangle, just in a geometric sense? It's length times width. So this has to be what we're looking at with f of x star and delta x. That has to be a length times a width, because it's the area of a rectangle. The way we're thinking about it, though, is it's a width, the width of the rectangle times the height of the rectangle. Okay. So delta x or f of x star, which one gives us the height of the rectangle?
X star?
Yeah, f of x star. So this is giving us the height of rectangle number 1. So let me erase all this other stuff. This was in 5.1. So this is the height of rectangle number 1. And then so delta x is the width of the rectangle, the width of the base. We said just for ease, we'll keep all of the widths the same. That's why we see delta x in every one of those. But what changes is the height of the rectangle, because the height of the rectangle is determined by the function. Like if I have this function right here, this rectangle defined here has a completely different height than this rectangle right here. But the height of the rectangle is determined by this function value right here. The height of that rectangle is that function value. So those are the things that vary, because your function varies. Okay, so that's our Riemann sum. Again, that gives us an approximation to the area. And so how would we make that exact? It's sort of alluded to down below. But if I put in 50 rectangles, I got a decent approximation. If I put in 1,000, I've got an even better approximation, right? If I put in 1,000,000, even better. So we're gonna do what to make that exact?
Use a limit?
Use a limit, right. So we don't want to stop with n equal 50 or 100 or 1,000 or 1,000,000 rectangles. We want to let the number of rectangles n approach infinity. And then that will give us the exact area. So I mean, you kind of see it there in the figure below, sort of a static image. I'll pull that back up. Now let's look at a simpler function. Okay, so here's, let's say, the area under x squared from 0 to 5, or 4.7. Let's just make it 0 to 4. Okay, so there's our Riemann sums with the n equal to 10. But then as we increase the number of rectangles, I mean, to just 1,000, it's a pretty good approximation to the actual area. And if we zoom in, we have to zoom in really far, we see that we're still missing little pieces here, but those little pieces eventually get filled in as we put more and more rectangles. So that's how we make the Riemann sums exact. It's just another limit, which again, we see the importance of limits in calculus. Without a limit, calculus doesn't exist. Like everything from algebra and trig, we just throw a limit into that, and now you have calculus. So it's really the heart of calculus is the idea of a limit. Again, illustrated here. Now notice they're a little bit funky with their notation. They say the net area is exact as n approaches infinity and delta x approaches 0. So that's just kind of the flip side. If I put an infinite number of rectangles into a region, delta x, remember, represents the width of the base of each rectangle. If I put in an infinite amount, just by definition, the width of the base has to go to 0, right? Because to fit more and more in there, we have to make it smaller and smaller. So I'll just make that note here as the number of rectangles which again is n, it goes or approaches infinity. The width of each rectangle, which is delta x, goes to 0. So they're really the same statement, just we're talking about a different thing. Does anyone have any questions? So then we actually here have our definition for a definite integral. And we'll notice that we see the same symbol we saw in 4.9 present here. But a function is defined on a closed interval is integrable. That's like a function that's differentiable. We can find the function's derivative. The derivative exists on this interval. Here we're saying that the function is integrable, means the integral exists on AB. And notice here how we define this. we defined the definite integral, looks kind of like the antiderivative of f of x with respect to x, but now we have these two numbers attached to the integral sign. So we go from a to b of this function with respect to x, and that's the limit as n approaches infinity on the Riemann sum, right? So the delta approaching 0, we can talk about that, but it's the same statement as n approaching infinity. And really, that's the one we're going to deal with, the limit as n goes to infinity, so don't think about that one. They're the same exact statement, but we're going to work with the limit as n approaches infinity. And so what this gives us, we saw that this is a Riemann approximation, a Riemann sum, which approximates the net area. Then we put the limit on it, which gives us an exact net area. So this is the net area. We can sort of put those pieces together at this point, but there is a lot of like theory behind relating an antiderivative to the area, which we haven't done yet. It's sort of implied here, but if we were the ones creating all of this stuff, say, hey, I think we're on to something, let's keep working with this. We would then at this point have to say, well, if I look at the net area being defined like this, does that really equal to all of this? And in this section, in 5.2, there's a lot of work devoted to showing the area, the net area, is actually related to the antiderivative of the function. However, we haven't made that connection at this point. All we know is that this symbol here, the integral from a to b of f of x dx, is just that sum right there. We haven't said anything about an antiderivative yet. Does anyone have any questions? So this is really giving us the other pillar of calculus, where we had the derivatives dependent on limits as one branch of calculus, and then we have these sums which give us the other branch of calculus. So as you might expect, that is an important definition. But let's talk a minute about the components of the definite integral. The next page we'll talk about this notation with the integral symbol. I guess I mean more specifically, let's talk about the components of this definition right here. So as we've addressed, the delta x is just the width of each rectangle. The f of x star sub k. So we're plugging in an x star sub k into the actual function. Whatever that function is, x squared, sine x, whatever. So when we evaluate this, what you end up with is a function of k. So this is just a function of k. I mean, it involves x's, but these x's have these subscripts, which are k's. And notice the sum operates on things that involve the k. So we have that sum from k equals 1 to n. And I guess we'll just say this operates on k. So really this sum from k equals 1 to n is operating on that function of n. or sorry, that function of k, f star sub k. F of x star sub k, my bad. Okay, go back up. So delta x is just some number, it's the width of each rectangle, it doesn't vary. This function of k that's in front of the summation, that's what's varying for us as k goes from 1, 2, 3, 4, 5, right? This thing is varying, but it's telling us that whatever this function of x star sub k is, that it has to stay in front of the summation because the summation operates on that function of x sub k. Okay, and once we compute this sum from k equals 1 to n on f of x star sub k, that gives us a function of n. For example, when we had the sum k equals 1 to 50 of k squared, notice the thing that's sitting out in front of the summation involves k. The sum is operating on that k squared. But when we compute that sum from the formula in 5.1, this said that it's 50 times 51 times 101 all over, what is that, 6? So notice how that sum has now become basically an expression involving the stopping point, right? The formula here was n plus 1 times 2n plus 1 all over 6. So in general, it just really depends on where we stop. Depends on that n value. But once we apply that formula, we now have the sum of k squared equaling a function of n. Okay. So we're looking at this as, or an expression of n, whatever. So this is our function of n in that particular case. Yeah.
Where did the 6 come from?
That's part of the formula.
Oh, it's just part.
Yeah. So that's kind of, this right here is kind of corresponding to this right here. Once we apply the summation formula to that thing, you've got an expression or a function involving n. And then the final thing to do is compute the limit as n goes to infinity. So that's where we're ending that. And that gives us the net area. So let's just call it whatever. This new, after we apply the summation, we get some function of n. We'll call it g of n. The last component says that we have to take the limit as n goes to infinity. So questions about that? That's pretty involved. So we should clarify anything that we need to clarify. And really, if you haven't looked at 5.1, then none of this is going to make any sense. Okay, so we're going to move on. So in the definition, the integral from a to b f of x dx equaling that limit, we broke down what the limit as n approaches infinity of the summation actually contains. As far as the notation here on the left, this piece of the symbol, the integral from a to b, is an infinite sum. Oops, sorry. Oh. So we're stopping at n and then letting n go to infinity. So basically the way it originated I forget who it was. It was either Leibniz or Newton. It came up with this, I think it was Leibniz, came up with this notation for this integral sign, and all it was an elongated S originally in his notes. And he elongated a capital S just to indicate that that was shorthand for an infinite sum, S for sum. So that's kind of what it's morphed into. It just indicates that we have an infinite sum. Let me do this. The dx on the other side corresponds to the delta x. And that just tells us with respect to what variable do we do all this to, right? So this is just telling us with respect to x. And then the a and the b are just the limits of integration. We're finding the area from this x value to this x value. So they're limits of integration. If you think about, we find an area on a specified interval. So A is our starting point, or value, if you will, and B is our ending. We have to remember in context of 5(1), that the x sub 0 is A, and the x sub n is equal to B. So really, we came up with the idea, okay, we've got Riemann sums, how do we make those exact? I put a limit in front of it, and then that notation's kind of weird looking, so let's come up with a better notation for that, and so we come up with the integral from a to b of f of x dx. Any questions about that notation, or what any of that means? It's sort of specified here as well. So for example, if we had the following Riemann sum, the limit as n goes to infinity, sum from 1 to n, 3x star sub k squared plus 2x star sub k plus 1 times delta x, on the interval 1, 3. I guess our question would be, what would this look like? What would it be in terms of an integral? Anybody have any ideas?
Is it like the S and then 3 on top, 1 on bottom?
So the integral from 1 to 3, yeah.
And then, without taking the integral yet, do like that function, I think, so 3x plus 2x plus 1.
Yeah, 3x. Don't forget the 3x is squared though.
Oh, right.
Yeah, but you're absolutely correct. Plus 1, is that it? Yeah.
Yeah.
We need our little differential there with respect to x. So now we know what that means. The specific example says, if I look at the function 3x squared plus 2x plus 1 on the interval from 1 to 3, then this right here is my Riemann sum, the limit as n goes to infinity on all of this, which gives me the net area under this function, between the function and the x-axis on that specified interval. Well, again, we haven't talked about how to actually compute this area, right? We know how to compute the area using the sums, so we could do it that way. But there is a shortcut way to do that, just like with the derivatives, right? The difference quotient and then letting h go to 0. That was really, really tedious to find the derivative of all functions. So then we said, is there a shortcut method? Yeah, there's the chain rule, the quotient rule, the power rule, et cetera, et cetera. And it's the same idea with this development as well. We look at it the long way first, and then we kind of make a connection between two things, and it allows us to evaluate this much easier. So there's our 3x squared plus 2x plus 1. And that's the area that we're finding when we compute that sum. Which we now know is represented by this integral. Or we should say the definite integral from 1 to 3. Does anyone have any questions at this point?
Delta x is like a constant.
Mm-hmm.
How does that relate to the dx? I'm just curious.
So how does the delta x relate to the dx? The delta x in 5.1 represents the length of each rectangle. So without getting into too much detail, it's quite advanced, but it's basically that we're just looking at some linear measurement along the x-axis. If we focused on this one rectangle in particular, we would say that this is delta x. This length right here is delta x. So the easiest explanation is because this is if we call this a function of x, then we want to find the area under that curve and the x-axis with respect to x, not with respect to y. We wouldn't want to find this area right here, or whatever. That's just a dummy variable. We could say f of t, and then the length of the rectangle now is delta t. But what it indicates is just a linear measurement along the independent axis. Does that make sense? So if anyone is majoring in math or going into higher math, you do see things like this where you integrate with respect to another function. And that's no longer a linear measurement along the x-axis. But for us, that's what it is. It's just the linear measurement, the distance from here to here. But the dx indicates that it's infinitesimally small, right? Because we know the length of these were going to 0. So it's kind of like when we had the notation for the change in y with delta y. Remember delta y from linear approximations? And then we said delta y was the actual change in the function, but then we looked at dy as f prime of x dx. And we said that's the approximate change. So it's kind of similar to that in how we go from a delta to a d. Any other questions? All right, so really the first way we're going to evaluate these things is to use geometry. Now this method is very limited. So we eventually, as we move past these, we start to look at a more, I guess, a robust way to determine. But the idea is once we know what this represents, if we can draw out the picture and it's some geometric figure, like a square or a circle or whatever, then we can just use a geometric formula to find the area. So let's start out from the integral from 2 to 4 on 2x plus 3. And so in words, what are we doing here with this problem? Anybody want to take a shot at that? Just in words, what we're doing.
We're finding the area under the curve on the function 2x plus 3 from 2 to 4.
Yeah. Is that what you're gonna say?
Yeah.
Okay. Yeah, so that's, we say under the function 2x plus 3, or rather in between the function 2x plus 3 and the x-axis from 2 to 4, what is that net area? So let's just draw this out. We have our linear function 2x plus 3. Here's the y-intercept at 3. I don't know, some line. Let me try to draw that better. Okay, so there's the function 2x plus 3. And we say that really the domain that we're looking at is from 2 to 4, so an x value of 2 to an x value of 4. And what we want is the area between the x-axis and that function on this region. Okay, so that's the area we want. So that's what all those symbols mean, is we're just finding that area. So really the geometric figure consists of a rectangle and a right triangle. So you could find the right triangle, the area of the rectangle, and add those together. There's maybe a lesser known formula for, figures such as that. That can be derived by just adding the area of the rectangle and the triangle together. But let's just look at the formula. We'll call the base H, one side A and the other side B. The area is 1/2 the base, so 1/2 H, times the sum of the sides, times A plus B. And that's exactly what we're dealing with here with this integral. So it says, taking this area, the length of the base is the distance from 4 to 2. So the base is 2 units long. And we just have to figure out the height of each side. So the left-hand side of this figure is going to be how tall?
That's 7.
Yeah, how do you know it's 7?
Plug in the x value.
Yeah, so plug in the x value of 2 into our function 2x plus 3. So that gives us a height of 7. And then the length of the right side.
11. Is it 11?
Yeah. So again, we're plugging 4, this x value of 4, into the function to get the height of that side. So then we just have what is the area of this figure, because the area of this figure is the integral from 2 to 4 of 2x plus 3 with respect to x. So the area is 1/2 2 times 7 plus 11. Which is 18. So that means the integral from 2 to 4 of 2x plus 3 with respect to x is 18. Does anyone have any questions about that? Yeah.
How would the units work out?
The units here?
Yeah.
Or just when we don't have any units here, we're just finding an area?
Yeah,
But, like, in
probably
general?
later on, but in general.
Okay.
what would the units be like?
I think I have a page in 5.3 reserved for that, but let's talk about it now. So let's go back to chapter 3. When we take a derivative, and we'll just call this independent x and dependent y. When we find the derivative, what are the units for the derivative, for a derivative?
Must be X.
Okay, let's put something then specific. Let's say the units on the x-axis are miles. Sorry, let's do minutes, and then let's y be in miles. If we find a derivative, what would the units be? Miles per minute, right? Yeah. Remember, the derivative is just dy, the change in y over the change in x. So the units are just the units of y divided by the units of x. I just mean units here, units of y divided by the units of x. Definite integral. Well, maybe we can. So the thing with the definite integral, though, it's. I guess we'll go ahead and talk about it. So here's x and y again. When we find the units here, what do? Maybe think about the Riemann sum and the definition of the definite integral. It's the limit of the sum of area of
Times X, right?
Huh?
It's just Y times X.
Yeah, right. It's y times x. How do you know that?
Because we're just finding an area.
You're just finding an area. Remember, y here was the f of x star. That gave us the height of the rectangle. Whatever, x star sub k. And then the width of it was just some value or measurement for x. It's f of x star times delta x in our summation. So it's just the units of y times the units of x. If we think about an area, right, this is a height times a length, or a length times a height, width times height, whatever. So x times y, y divided by x for derivatives. So the units here, we would just say square, square units, whatever is an area. And maybe then you can think about, okay, well, if I have the graph of a position and I find its antiderivative, position in miles per minute, velocity in miles per minute as the derivative of position. Maybe if you think about what if I graphed a velocity and looked at the integral of velocity, that should give me back to position. So then you can maybe think of the units that way in both contexts as a specific example. Okay. Any other questions? Okay, so how about example 2? So unlike the first example, we immediately recognize 2x plus 3 as a linear function, graph that, find the area. What kind of function are we dealing with here? What does it look like?
Circle.
Yeah.
Half circle.
So that's our function, f of x equals y, y equals f of x. So how do you know it's who said half circle? Half circle, top half or the bottom half?
I would think top, because it's positive.
It's positive, right? So the way we see that, y is the square root of 1 minus x minus 3 squared. We square both sides. Put y and x together. So I'm going to write it this way. On the same side. So we have x minus 3 squared plus y squared equals to 1. Hopefully we recognize that as the equation of a circle whose center is where?
3-0.
3, 0. Circle center 3, 0 with a radius of 1. But that's sort of half the story. Because notice if we just start here with the equation of a circle center 3, 0, radius 1, we have this equation. And we say, well, if I solve for y, what I would actually get, in other words, if I start here and work back this way, what I actually get when I solve for y is both the positive and the negative square root. So the positive root when y is positive is the top half of the circle above the x-axis, and the bottom half of the circle when y is negative is given by the negative root. So since we're dealing with the positive root, it's only the top half of the circle. So let me draw this out. So that equation is described by this function, and this one is the negative root. Sorry, I probably shouldn't have centered that at 0, 0, because that's not accurate. I'll just get rid of those lines. So we only want the top half of the circle.
I have the answer. I have the answer.
Okay, what is it?
Pi over 4.
Right. So let's make a note here that it's also the top half of the circle. I'm gonna erase this stuff here. So that's it. What are we actually looking at? We need to draw that out, just so we're not computing the wrong thing here. We have a circle that's centered at 3, 0 with a radius of 1. So we're going to go out to 4 in this direction, out to 2 in this direction. Have our circle. So now we know what equation we're actually dealing with in front of the integral. You got to go back to the integral because it says the domain or the bounds are only from 3 to 4. So the area that we're looking at is this area here. So that area is only 1/4 of the circle. So 1/4 the area of a circle. remember the formula for the area of a circle? I guess you kind of have to at this point, otherwise you can't progress. So that's the area of a quarter circle, area pi r squared, for the area of a circle, and our radius was, we determined, 1. So we have 1/4 times pi times 1, or pi over 4, as the area. So if any of you are going on to Calc 2, you'll see a specific way to figure that out, but I honestly think that even once you have that technique, that this is a much easier technique. I mean, it looks kind of funky, but it's really very straightforward approach to finding that integral. The other approach is long-winded. It's kind of tedious. Okay, so questions on that example? So, and then the problem, the limitation with this is, what if we had a function, you know, from 2 to 4, let's say, that look like this? Then there is no geometric formula for that. So that's why that method is limited. We've got to come up with something better than just using geometry. So we're going to look at a couple of properties of this area, this net area kind of thing, and then we'll talk about, as a general sense, how do we compute these things when they're not a geometric figure. But a few properties first. This example here is to kind of give us an idea of what we're dealing with when we compute these definite integrals. So we're given this figure. Let's find let's find the integral from a to b and on this function f of x with respect to x. So what would that be? What? From a to b. 12. It says find the net area from the axis to the function between a and b, and that's given to us as 12. Maybe I should put this up here. Does that make sense? It gives us a visual of what we compute, something that can result when we compute this integral. Example 2, what is the integral from b to c on that function? Negative 10, what do y'all think? Negative 10?
I think it's positive 10, right?
Negative 10 or positive 10?
Well,
Right, yeah, it's below the x-axis. Who said that? Below the x-axis, it's negative 10.
I'm not, I'm just.
How about the integral from a to d of f of x dx? 10. Yeah, how'd you get that?
Because you add 12 and 8 and then subtract the 10 from the x-axis.
Yeah, good. So that's the total net area from a to d. Remember, that's the area above the axis minus the area below. Do you have any questions about that? Some kind of visual reinforcement of the symbols. So a couple of properties here, the reversing of the limits and identical limits. The first one is if we reverse the limits. So going from b to a of f of x dx is equivalent to negating and then going from a to b. So if we switch the limits of integration, you have to multiply all of it by negative. Maybe once we talk about the fundamental theorem of calculus, we could justify that pretty easily. But for now, maybe think about just going in reverse. I don't know. And then also the integral from a to a of f of x dx is equal to 0, because from a single point to the same point, there is no area under a curve there. That's like saying, you know, from on this function, basically, what is the area of a line? There's no area. So to be honest, those aren't utilized a lot for us. In fact, I don't know that in practice, that we ever use those. But there are some questions that we'll see have you kind of utilizing either one of those, just to get you used to it. The other properties that aren't mentioned are properties that are directly related to our summation properties. Because remember, this integral from a to b with respect to x is nothing more than a sum. It's an infinite sum. So the things we can do when we add stuff together is what we can do when we take an integral from a to b of something. So if we have the integral of a function plus or minus another function, then just like with the sum, with the limit, with the derivative, those things got distributed through. This is equivalent to the integral from a to b on f of x with respect to x, plus or minus, whichever is present, the integral from a to b on g of x dx. Just like we saw with antiderivatives as well. And then the integral from a to b of a constant times f of x dx. Just make a note here. C is a real number. We can pull the constant out and multiply it in once we compute the integral from a to b of f of x dx. So I hope those properties aren't mystifying in any way. We've seen those applied to many different operations. Do y'all have any questions at this point? Any comments? Anything? All right, we'll take a break and then look at how we compute these without geometry. See what's next. All right, so an example there to work with some of those properties. We're given the integral from 0 to 5 on the function is 3, and 0 to 7 is negative 10. We want to find a few things. First, the integral from 0 to 7 on 2 times f of x. So the integral from 0 to 7, 2 times f of x dx would give us what?
6.
2 times f of x, 6. Do y'all agree? So remember, this constant times that function is being pulled out. And so we just have 2 times the integral from 0 to 7 of f of x dx, which was given to us as 3. So it's just 2 times 3, which is 6.
Why if it's from 7 to 0?
Oh, 0 to 7, yeah, 0 to 7. 2 times, not 3, but negative 10, yeah, thank you. So 2 times the integral from 0 to 7, 2 times negative 10 is negative 20. How about the integral from 5 to 0?
Oh, no, negative 3?
Negative 3, right? We've switched the limits of integration. From 0 to 5 is 3, so from 5 to 0 is negative 3. Does that all make sense? Okay, how about the integral from 5 to 7?
Negative 13.
How do you know it's, how do you know?
So, it's just, maybe it's not.
What did you do to get negative 13?
So from 0 to 5, instead of up, is to 3.
Mhm.
But then on the second one, it's 0 to 7, which is negative 10. So the next two, like 6 and 7, would have to give us negative 13 more.
Okay, yeah, I mean, I think,
Maybe my logic is just wrong.
You could do 0 to 7 minus 0 to 5.
yeah. Yeah, so I think initially you're thinking about it correctly, but there's nothing that guarantees that the integral from 5 to 7 is whatever that is to make that negative 13. I mean, it's definitely a possibility, but it's not guaranteed. So, Aya, what did you say?
So it's the same function, so 0, you can take what 0 to 5 is.
Okay, from 0 to 5?
Is 3. And you subtract that from 0 to 7.
From 0 to 5, we know is 3. But then we also know that the integral from 0 to 7 is negative 10. So what that means is if I go from 0 to 7, I'm accumulating from 0 to 5 and then on to 7, but I get a negative 10. So that tells me that there's more area below the x-axis if I go from 0 to 7 because I get negative 10. The net area there is negative. So, you know, this if I have to take 3 plus something and get negative 10, right? Because I don't know what this looks like. This integral, this could be, you know, it could be positive here, and then it could be like really negative, or it could just all be negative. You know what I mean? Like there's no, it's sort of indeterminate at that point. But we know that the integral from 0 to 7 is negative 10. So if I accumulate that area less than 3, what would that have to be? So it kind of turns into an algebraic problem, right? What do I have to add to negative 10 or to something plus negative 10 gives me that 3? Or I said that backwards. So if we think about the total, the integral from 0 to 7, as the area from 0 to 5, this is 0, plus the area from 5 to 7, so maybe, Matthew, that's how you were thinking of it?
I think that's pretty true.
We're given this area here as negative 10. We're given the area from 0 to 5 is 3. And then we're solving for our unknown. Okay, so Matthew, if you said that, I didn't quite catch all of it, so I apologize. If that's how you were thinking of it, though,
Yeah,
that's
how.
that's correct. So then we just solve that equation for our unknown. So we subtract 3 from both sides. So if the integral from 5 to 7 is negative 13. Okay. Do you have any questions on any of those? All right, so those properties out of the way, then we'll look at how do we actually evaluate that when it's not a geometric figure. And the way we have to do that is we have to go back to the definition, which is this limit of the sum. We have to figure out what all that stuff is. So honestly, I said it's the long way because this is equivalent to finding the difference quotient, simplifying, and then letting the h go to 0 to find a derivative. There's a long way to find a derivative. This is the long way to find the definite integral. So we're using that definition right here to compute this. And so to make our computations a little bit easier, we're gonna choose the f of x star not to be the midpoint Riemann sum or the left Riemann sum, because those involve the k minus a half and the k minus 1 respectively. We'll choose the f of x star to be the right Riemann sum, which was just a plus k delta x. So really, like we said, the components of that are the function f times delta x. Remember from 5.1 that delta x is just the length of the entire interval divided by how many rectangles we're putting in there, so it's b minus a over n. We're using the right Riemann sum defined in 5.1 as a plus k delta x for our delta x star, because that one didn't involve the minus 1 or the minus 1/2 like the left and the midpoint did. So it is the simpler of the 3 Riemann sums as far as the formula goes. And then so we're going to use those two components. We're going to compute that sum of the function of k, which turns into a function of n, and then we're going to compute the limit as n goes to infinity on that expression for n. So with that in mind, then we can kind of reformulate our working definition of the definite integral with putting our right Riemann sum in here, a plus k delta x for x star. That's the right Riemann sum. Okay, so that's our working definition. If you're asked to compute the integral from a to b and f of x dx using the definition, this infinite sum on the right is what you have to use. That is the definition of the integral. So the delta x is just going to be some expression that involves n. Like we said, the summation operates on things that involve k. So the only thing that has to stay in front of the summation is the f of a plus k delta x. That has to stay in front of the summation. Once we compute that in step 2 by the formula, the sum of f of a plus k delta x turns into some expression involving n. And just so we're not confused here, let's call that g of n. It's not the same as the original function, g of n. Some new function of n, and then the limit is the last thing that's computed. And then once we compute that, that's going to give us the net area. Again, notice in that definition, there's really only 2 things to find. Everything else is simplifying. All we need to find is delta x and f of a plus k delta x. Everything else in that formula, we simplify the sum and then compute the limit. So let's look at an example and practice how that comes about. I'll just rewrite the definition here. So that's what we're trying to figure out, what these components are on the right-hand side of that equation with this specific example from 0 to 2 x squared dx. So the first thing, we're going to find delta x. Notice we need delta x first because delta x is present as a multiplier of the summation, but it's also present in what we're plugging into the function. It's f of a plus k times delta x. So your first step is always to find delta x. And delta x is defined as b minus a over n. So b is 2, a is 0. Remember, n is n, because the last thing we do is let n go to infinity. So unlike in 5.1, when we had 50 rectangles, n was 50, or 35 rectangles, we divide by 35. Here, with the definition, we just leave n as n. Okay, so delta x is 2 over n. And then before we can evaluate the function at a plus k delta x, you need to find what a plus k delta x is, and then plug that into the function. So our a is the lower limit here, 0. K is still k. Remember, this function is going to be of k times delta x. So there's our a plus k delta x, which just gives us 2k over n. Now we have to take a plus k delta x and plug that into our function to evaluate f of a plus k delta x. Notice here the function given to us is just x squared. So whatever we plug into f of x, it just squares it. So since we're evaluating f of 2k over n, we just have 2k over n squared. So we got 4k squared over n squared. So there's f of a plus k delta x and delta x. Those are the two things you need to find to work with that definition. So now we're going to take those two things and put it all together. So we're computing the limit as n goes to infinity. And the sum from 1 to n of f of a plus k delta x times times delta x. As a way to compute the original integral. Does anyone have any questions at this point? As a reminder here, the limit operates on things that involve n. The sum operates on things that involve k. So let's reconfigure this so that it's a little bit more in line with what the operations that we actually need to perform. So I'm just going to simplify our expression first. We have the limit still of the sum. Oops. We've got 8k squared over n cubed. And so from this point, what I'm going to do is, since I've kind of simplified that expression, anything that involves a k, I'm leaving in front of the sum. Anything that involves an n, I'm leaving in front of the limit. And anything else I can put out in front of all of that. So the 8 doesn't involve a k or an n, so we're going to put the 8 out in front of the limit as n approaches infinity. The only thing that involves an n is the 1 over n cubed, so we're going to put that out in front of the limit. And then what's left over is the sum of k squared. So that's what we want to, when we're given a problem like this, you want to try to work it down to that place where we're at right now. Things involving the sum with the k's together, limits with operating on n, and any other constants out in front.
That's our final answer.
No, we have to compute the limit as n goes to infinity of all that stuff. So now here's where we get, basically there's one way to do this, but the theorem from 5.1 with the summation formula is a little bit more tedious, and the formula that's not in our textbook is a little bit easier. So before I actually pass these out, we're going to look at this through the lens of summation formulas from 5.1. So this is what we're going to focus on. We're going to look at two ways to evaluate it. One's a shorter way, one's a longer way. Summation formulas. Formulas. Now, the summation formula from 5.1 tells us what that sum is. So that's the first thing we're going to address. You always address the sum part. With this longer way anyways, you address the sum portion first. So does anyone remember that summation formula? You probably didn't remember it because you maybe didn't know you had to. But derivative of that. I'm just gonna write this part down first.
Talking about the sums and powers of integers, right?
Yeah, the integer squared.
So it's n times n plus 1 times 2n plus 1 whole over 6.
The formula up to n is n times n plus 1 times 2n plus 1 all over 6. So you see, once we've computed that sum via the formulas, we now have an expression involving n, and we can compute the limit as n goes to infinity on all that stuff. So here's where you could use L'Hopital's rule, right? Because we have the limit as n goes to infinity, denominator infinity cubed, the numerator infinity times 2 times infinity. So that's infinity over infinity, but it's a polynomial in the sense of n. I think it's easier, since we're looking at a limit at infinity, just to look at the leading term in the numerator over the leading term in the denominator. So we have 8 times this limit. Now we're going to combine this stuff here. So we're just going to expand out the top, multiply the bottom. So we've got 2n cubed plus 3n squared plus 1 all over 6n cubed. So what would that limit as n goes to infinity be? Yeah, 1/3. If you're not sure, use L'Hopital's rule. To use the L'Hopital's rule a couple of times there, but from other, I should say chapter 2 rather, all we have to do is look at the leading term over the leading term, because it's a limit at infinity on a polynomial expression. So that's equivalent to the limit as n goes to infinity of 2n cubed over 6n cubed. And so that limit just turns into 2 over 6 or 1 over 3, which is 8 over 3. And that's 2n cubed plus 3n squared plus n as the last, n times 1 times 1. So the integral from 0 to 2 of x squared dx, the area from 0 to 2 on the function x squared is 8/3. So questions on this here? All right. So then, using this theorem, once we've kind of separated it here like we were prior to the other summation formula, according to this theorem, what would the limit as n goes to infinity of 1 over n cubed sum of k squared equal? Right. So that theorem gives us all of this stuff. That theorem tells us all of that stuff is 1/3. So you don't have to remember the summation formulas for k, k squared, k cubed using that theorem. But notice the pattern here. It has to fit the pattern. In general, the power on k is 1 less than the power on 1 over m. Or sorry, 1 over n rather. So if you look at those specific examples, you see that's true through all of those. And so that limit equates to the 1 over the power that's attached to the n in front of the summation. So if you just want to remember those instead, I'm fine with that. I'm not going to require you to remember the summation formulas from part 1 from 5.1. I think this is easier in practice to remember than those summation formulas. So either way you go though, I think the most difficult part is just getting this all set up correctly. So are there any questions on either method? Yeah?
If that's given on an exam, do you have to write like that you use this, or can you just write the answer?
Yeah, you just go from here to here like we just
Okay.
did, yeah. Yeah, I'll know what you did. Okay. Yeah, any other questions?
We can write this formula on our note card, right?
No. So the thing with the note card is the new material that we haven't tested on cannot be on your note card. The note card is only applicable to old material that we've tested over already. Yeah. Okay, let's do one more. Modify the function a little bit. We'll see what changes it makes. Ilya?
So, looking at this sheet, if we get something that has like 1 over n to a power, and that power doesn't match 1 power less of the k. Oh wait, never mind. Never mind. Answered my own question. Sorry.
Okay. Yeah, if you didn't get that, then if you don't have that pattern, then it's difficult.
It's wrong or difficult?
Well, so like if this were like 1 over n to the 5th times sum of k cubed, it wouldn't be 1/4. You would have to work that out.
Okay, so it's possible to get something that isn't like in this format.
It's possible, but not likely at all.
Okay.
For us, not likely. So let me write the definition down so we know what components we need to fit into this definition. I keep doing this, sorry, just habit. That's an N. F evaluated at A plus K delta X times delta X. So like we said, the first thing we're going to do is find delta X. Delta X is still the same. We have the same region from 0 to 2 within subintervals. So delta X is 2 minus 0, B minus A over N. Still 2 over N. The thing that changed is the function, which is going to alter f of A plus K delta X. Find delta X. Second, find A plus K times delta X, so we can put that into the function x squared minus 1. So again, A is 0 plus K times our delta X gives us 2K over N. Just note here the function squares and then we subtract 1. We've got our A plus K delta X. Then we're going to plug that into the function. So we're evaluating f of 2K over N. So we're going to square the input and then subtract 1. So remember, the f of A plus K delta X, whatever expression you end up with, has to stay in front of the summation. There's a tendency for people to say, well, part of this, the minus 1, that part doesn't involve a K, so I don't have to sum that up. But that's entirely incorrect. Whatever results as f of A plus K delta X, you have to sum all of that up, even if there's constants in there that don't involve K. That f of A plus K delta X has to stay in front of the sigma. So then we have the integral from 0 to 2 of x squared minus 1 dx is the limit as n goes to infinity, the sum from 1 to n on our 4k squared over n squared minus 1 times our delta x. So here I'm going to write this out again. Does anyone have any questions? So here, again, we'll do the same thing we did in that last one. We'll combine all of these things, see which terms involve K and N, and deal with those respectively. So the first thing we're going to do is distribute the 2n into the brackets. So we still have the limit n going to infinity from the sum from 1 to n. And then we're going to multiply the 2 over n times the 4k squared over n squared to give us 8k squared over n cubed. Distribute the 2 over n to the negative 1 to get minus 2 over n. So the reason this one's a little bit more difficult is because than the last problem just had the 8 k squared over n cubed. This one has 2 terms that we have to sum and take the limit of. So I guess there's a couple of things we could do. What is anybody thinking of something specific that we would do from this point?
Take the 8 out of front.
Yeah, so but before we take the 8 out front, we have to consider that we would be taking the 8 out of the 2 over n and the 8k squared over n cubed as well. So you could find a common denominator and just combine all of that, right? Then you would have something plus something else over n cubed. But then could we break that up? We probably could. Just a bunch, remember the sum of a bunch of sums is the sum of each term? So I don't know, maybe you can find a common denominator and work with that. But we've got the limit as n goes to infinity of the sum of all of this stuff. So let's just look at those individually. In other words, this operation of the limit and the sum out front, let's put to both of these. So we have the limit of the sum of 8k squared over n cubed minus the limit of the sum of our 2 over n. And then we can just look at those individually. Is everybody okay with that? I mean, really the limit doesn't technically need to be there because that's just the last thing we compute. So maybe to make this a little bit more clear, we should just first deal with the sum of that stuff. You can leave it like this if you want. I think I'm gonna erase the limit part just to make it a little bit more clear, because we had the formula that if we've got the sum of a sum or a difference, that can be distributed across the sum or the difference. So I think we'll just leave that in our notes like this and leave the limit out front. Honestly, it's all the same. Whichever way makes more sense to distribute the limit and the sum, or just the sum first, go with that. So are y'all okay with where we're at? Okay, this sum, 8k squared over n cubed, we already dealt with that. So we could go with the long route and find the formula for the sum of k squared that we did in the previous example. Or we could just refer back to our previous example and say, if I take the limit as n goes to infinity of that sum, what do I get? Yeah, that's 8/3. So really we just need to take our 8/3 minus the limit of this sum. So that's the thing, if you're going to use the formula on the handout, that formula involves a limit and a sum. Okay. So that's the limit of, and now we're back to the step I just kind of erased, but that's the limit of this sum minus the limit of the other sum. Again, we know this to be 8/3 from our previous example. And then let's compute what is the limit as n approaches infinity of the sum of 2 over n. Minus 2. Does everybody agree that that's 2? I mean, that 2 now is a constant that we can put out here. We're summing from k equals 1 to n of 1 over n. Notice the expression 1 over n doesn't involve a k. So the summation is not affecting that 1 over n. So So I'm just gonna scoot this down a little. So we have minus 2 times the limit as n approaches infinity. The 1 over n stays in front of the limit, but outside of the summation. Sorry, this is 1 here. If we factor out, or we take out that 1 over n. So now this fits the first line of that theorem. The limit of all of this stuff is just the power on n, which is 1. So what we have is our 8/3 minus our 2 times 1. Okay, so we've got 8/3 minus 2, 8/3 minus 6/3. That's 2/3. Okay, so the net area from 0 to 2 on x squared minus 1 is, from the function to the axis, is 2/3. Does anyone have any questions on that example? So, to be honest, one like this, or the last example, will be on the final. But we are looking at, moving forward, easier ways to do this. We don't have to take a limit of a sum. So that's really what 5.3 is about, is how do we make all of this simpler? What's the shortcut to do all of this? Any questions on 5.2 at all? So a lot of this stuff from 5.1 and 5.2 are really technical. The only thing on the final from 5.1 and 5.2 is going to be one of these types of examples. Most of Chapter 5 material is really coming from 5.5. Once we get to 5.5, that'll be the majority of the final for the new material. So we'll stop there to do these evaluations. Please try to look over 5.1 if you haven't done so already.